In the previous sessions, we talked quite a lot about the idea of how to convert or translate problems, computational type problems, into an equivalent form where to solve your computational problem you would look to see whether a particular string belonged or did not belong to a particular language. So it was a sort of kind of conversion from presenting a problem in a computational way, a kind of direct way, and a more indirect seeing whether a particular string belongs to a language. So from a computational problem to a language belonging type problem. We've talked about that at length, so I won't go into that again. And this board effectively, and several more boards, not just sessions, 4 sessions per board, we will use that idea and just giving one theorem after the other and showing that a whole series of languages are decidable. Remember, a language is decidable. I mean, I say this quickly because it's easily done. A language is decidable if there's a Turing machine or an algorithm. They're the same thing nowadays. At this stage into the text, that there is an algorithm, there is a Turing machine that accepts every string in the language and rejects all other strings. Okay. So it's the Turing machine is a decider. It decides, so it never halts. Sorry, it always halts. It never loops. So in other words, it always either accepts or rejects. And so you convert your problem into a language type problem. And then you find a Turing machine that accepts all the strings in that language and rejects all the others. So you construct. So it's a proof. You're proving by construction. Proof by construction. Finding Turing machines, constructing Turing machines that are deciders for that language, and hence the language, by definition, is decidable. Okay. Alright, well we do a few more. Previous board we dealt with regular languages and the machines that go with regular languages, and they are finite automata. So we dealt with 2 kinds. The deterministic finite automata, DFAs. They're ones which at each step, as you're going through the steps, you transition from one state to one other state. There's only one next state, so it's determined. What the next state will be is determined. It's determinist. So it's a deterministic finite automaton. And then we did non-deterministic finite automata, NFAs, where it's possible to have more than one next state. And we also did we did theorems each of those. The computational problem each time was asking whether a particular automaton, or either a DFA or an NFA, or could a particular finite automaton accept a particular string, for an arbitrary automaton and an arbitrary string. And so he wrote something of this form, where that, well, in this case is a particular instance, but talking generally, this here was some kind of machine, an automaton, and this was a string. And the question was, could this machine detect that string for an arbitrary orbit? And we created a language where this ordered pair, so the given machine and the given string, if this machine could detect that string, then this ordered pair was a member of this language, a member of this set. Remember, a language is just a set of strings. Okay? And this is a string because we've represented it, we've encoded it in such a way that information about the machine and the string is put into linear form, string form. Make a string out of it. Okay? So if you have a machine, a Turing machine that decides this language, that means you can use that machine to see if this string here belongs to the language, and you can construct, design a machine that tests that. And it's the machine is a decider. Right? Either this does belong to the language or it doesn't. That's it. And so it either accepts or rejects. So by definition, it's a decider. All right. Well, let's continue on doing much the same kind of thing. So we're using this technique that will carry pretty well right through the chapter. So it's a basic idea from previous board of converting a computational type problem into belonging to a language type problem. So we'll keep that same strategy. Now, in this particular case, we're getting on to the next theorem, and on this board, how many theorems? So 1, 2, 3, 4. In the beginning of a fifth. So, and they're all much along these lines. And what changes each time is the language that you're talking about. So this case we're talking about the language here is Rex, R-E-X. That just R-E-X short for regular expressions. Okay. Remember, from regular expressions you can generate a string. Okay. Okay. So we start with a computational problem. We want to know. We want to create an algorithm that can decide yes or no whether a given string, some arbitrary string, can be generated. I'm getting hot. It's amazing. It's getting close to no. What's the date today? Just a minute. Yeah, in a week's time it'll be November. So you think it'd be starting to get a bit cooler, but I'm still hot. And see, I'm in the southeast coast, little city of China in Xiamen, and the weather here it must be, I don't know, 20, 22, 23, 24 degrees centigrade, and when I get, see, normally I don't wear shorts or shirt. I'm just in underwear because it's quite warm. And I put this stuff on, and now I'm getting hot and sweaty. So I'm going to see if I can find the remote. Yesterday I had the same problem. I could not find the remote. My wife hid it somewhere. So if I can find it, I'll switch on the AC. So just a minute. And close the doors. Okay, so that should help. Right, so now the R now is it's not a machine. We're not talking about automata now. Now we're talking about, well, we're moving into things like regular expressions, and later we'll do context-free grammars and stuff like that. But it's a similar type of problem. So the computational problem is, can this regular expression generate a given string? That's the problem. And then we translate that problem into, does it belong to a belonging to a language type problem in this form. So this is a language we generate, okay? And this element belongs to the language, to the set, if this regular expression can generate the string W. Okay, so this would be an infinite string. It's for any regular expression, an infinite number of them. Any string, an infinite number of strings. It's an infinite language, and we're trying to find an algorithm that would answer